the second most abundant natural polymers, and it can be used and improve the sustainability of the plastics by decreasing the dependence to fossil-based materials.
My name is Omid Hosseini. I work as a researcher at RISE Research Institute of Sweden. I work on biomass valorization, bio-based material, especially lignin-based materials. So we work on different materials or different products from lignin. So what is needed is to modify lignin based on the target application. For example, if you want to make fuels or chemicals from lignin, other materials like thermoplastics or different carbons from lignin.
We are at our laboratories at Drottning Kristinas väg, where we modify lignin and we make coatings with it and coat paper and board with lignin.
This is one of the wet spinning labs at RISE. Here we develop fibers from renewable sources, mainly from lignin and cellulose. The fibers can be used in several applications, for example as a precursor for carbon fiber, textile fiber development, and also fibers for biocomposites.
So one area we work is carbonized materials from lignin, and one application of the carbonized or material is using this material in energy storage application. I mean, you know that the demand for energy is growing and the need for the renewable sources or more efficient ways, for example, using batteries for storing the energy is increasing. So here is this is the car that we, as a demonstrator, we made it. So in this car we have different components made from lignin-based carbons. For example, the roof of this car is made from the lignin-based carbon from the melt spinning process. And also in this car we have lithium-ion batteries, and these batteries are inside the car, and in these batteries we use a lignin as anode electrode for the lithium-ion batteries. This is to show different applications from lignin, both structural and non-structural, which is energy storage applications.
My name is Erika Back and I work as a research engineer here at RISE, mainly with chemical analysis of samples from the pulp and paper industry. One of our techniques that is very useful is pyrolysis GCMS, in which the samples are heated rapidly to high temperatures in an inert environment. In that way we can identify the chemical structure of any organic material, such as lignin.
Lignin is a fantastic material. It's beautiful, it's brown like chocolate, and it's full of functionality, so we can do a lot of wonderful things. And we just need to be each day smarter about this. It's fantastic.
Hi everyone, and very welcome to our webinar this afternoon. Afternoon in Sweden, perhaps morning or evening elsewhere in the world. You're all very welcome, and one of the speakers today you saw in the film, that's my colleague from RISE, Peter Rättö, and our second speaker today is Pedram Fatehi from Lakehead University, Canada. So especially welcome to the two of you. As you probably have noticed, we are recording this event, so later on you can find it on the website from LignoCity, where also all the previous webinars are to be found. And what you also can find there is a digital tour, so you can visit our location wherever you are in the world. And to make the experience best out of this event, on the upper right corner on your screen, you have the possibility to change view of your screen between speaker and gallery view. So you can try that out for yourself and see the difference from them. And my name is Maria Ulmhult, and I work as a project manager at RISE and our testbed LignoCity. So what we do is running several projects, and one of them makes those webinars possible. It's called Lignin-Innovation, and it's in collaboration with the municipality of Kristinehamn and the Paper Province as main partners. And it's also financed by the region Värmland and the Swedish Agency for Economic and Regional Growth. So very glad to see so many of you here today, and I hope you will write a lot of questions in the chat that we kindly ask you to do. And after the speakers have made their separate presentations, we will respond to as many of them as possible. So type in the chat, and you find that one in the bottom of the screen. There you also have a bottom of reactions that you can use if you like meanwhile. After 3 o'clock, when the webinar ends, we will stay for 15 more minutes, and then we will have a chat together with those who decide to stay. So if you have time, take 15 minutes extra after the presentations. Now I want to introduce Peter. How are you this afternoon?
I'm fine, thank you, Maria.
And you are located where in the world?
Well, actually, I'm sitting in Stockholm, so that's not too far from Värmland.
That's a good place to be. And you're not only a movie star in the film we just saw, you do a lot of interesting research. So please introduce yourself and share your presentation, because we want to know more. And again, everyone who has questions, please type them in the chat, and you find the bottom for that at the bottom of your screen. And we also happy to read encouraging words there. So feel free to write in the chat. And Peter is sharing his presentation. And to see that one in the best way, you use the view speaker, and you choose yourself on the upper right corner to find the right bottom. Now, Peter, we see your presentation perfectly well. So please introduce yourself a bit more, and we listen to you.
Thank you. My name is Peter Rättö, and I'm a senior researcher at RISE, as you probably have guessed. I'm colleague with Maria. I'm sitting most of the time in Stockholm at Drottning Kristinas väg. And well, I have a background within coding and printing, but I went from there on to barrier coding. And lately, well, I wouldn't say lately, but I've tried to somehow take an interest into the raw materials and how to connect biorefinery into barrier coatings. I also hold an adjunct professorship at Lakehead University in chemical engineering, and an associate professorship at KTH, polymer and fiber technology. But today I'm going to be talking about lignin oil emulsions as barrier coatings. This is actually work we presented at the Material Research Society in May this year. I have two co-authors, Dimitar Valtakari and Christina Janell, been involved in this work. If we look a little bit on the background, we have a background. Well, if we look at packaging materials, fiber-based, you usually put the barrier, or you need to put the barrier in order to either protect its content or to protect the board material itself, since it's quite moisture sensitive. And that makes that you usually need both an oxygen and moisture barrier or water barrier, and that has a tendency of becoming tricky, which ends up that you either put an aluminium layer combined with a polyethylene layer, and the polyethylene layer here is more or less for heat sealing, or you have a multi-laminate consisting of polyethylene and some other plastic that makes a very good oxygen barrier like EVOH. These are usually extrusion-coated substrates. So when you're trying to reslush this in recycling, you end up with quite a lot of the barrier into the reject, which is burned for incineration and recycled to fibers. Let's see if I can switch to the next one. As I said, the reason why you're using this complicated structure is that you usually have, when it comes to polymeric materials, a good oxygen barrier like cellulose, which has a quite low oxygen permeability, whereas the water vapor transmission rate is quite high, which means it's a poor water barrier. Or if we put like polyethylene, you have a very low water vapor transmission rate, but you have a quite high oxygen permeability. So you have a good water barrier, but a bad oxygen barrier. And you have quite a lot of materials in between, but finding materials that have both low oxygen permeability and water vapor transmission rate is a little bit harder. PVDC is one of the exceptions here, and if you go to something more extreme, to look at liquid crystalline polymers that really are quite good but expensive and hard to process. As I said, most of these are applied with extrusion coating, put the plastic melt on a board, and you need some materials that is formable. I think this one is probably PBS or polyethylene that we're putting here from an extrusion coater. But it places quite a lot of demands in terms of processability and thermal stability of the polymer itself. And let's face it, if we look at something like cellulose or lignin, we're probably not really there that it has a perfect behavior for this kind of process. What you also can do is that you can put it in a water carried phase, and you make a dispersional solution in water with the barrier material. And this is something that you can do with polyvinyl alcohol as an example. Starch or cellulose is also possible, or hemicellulose. And then you apply it in a regular coater, whether it's a blade coater, a metering size press, or a curtain coater. All these are a little bit trickier, but in its own way. But generally, if you can get to here, you can actually put your barrier online in the paperboard machine. Then it comes to the issue of replacing the fossil-based materials. That's one of the main questions that we actually get together with recycling when it comes to barrier materials. Thing here is that we have quite a lot of bio-based materials that are quite good oxygen barriers, and they're water soluble, but they're have a quite bad moisture resistance. Cellulose and non-cellulose is a typical example of this. If we look at these are actually nanocellulose films. If you just have the nanocellulose film, you can see that you have a quite hydrophilic surface, and this water drop will actually dissolve into the surface later on, or the nanocellulose. Whereas if you put a water barrier on top of it that is hydrophobic, you can see that you have a totally different shape of the drop, that it's more or less water repellent, and you don't have the things, the water dissolving into the film here. This is actually a cross section of this film where you have the barrier layers on each side and the nanocellulose in the middle. You can also have thermoplastic materials that are bio-based, but these tend to, and I just say general, are quite expensive, and they're not really that thermal stable though as polyethylene, and hard to process. But this is in general. I'm not going to go into any particular materials here. There might be exceptions here, of course. So if we kind of look at the issues that we're trying to get to tackle within barrier research, is that we have quite a large demand for recyclable packaging materials. The Evergreen initiative within Europe is one particular example of this, that we really want to somehow be able to throw everything in one recycling bin. There is also a wish to replace fossil-based materials with renewable alternatives. The first one, again, in quite general terms, dispersion-coated materials tends to be easier to recycle than extrusion-coated materials. The second one, when we look at replacing fossil-based materials with renewable alternatives, for oxygen and grease barriers, that's quite, we have alternatives. We don't have that many alternatives when it comes to moisture barriers. Also, when we look at good water oxygen barrier, we use multiple laminates to get the best of each material here. But that tends to be a little bit harder to recycle. What I have seen is that we have quite a lot of water barriers that are fossil-based. There are, of course, exceptions. In that case, you can put wax-based barriers, so on, as water barriers. And also that good water barriers, well, in order to have a good water barrier, you need something that is probably hydrophobic or at least water resistant. And that would mean that you will quite probably have a limited solubility in water. Now, if we look at lignin, which is one of the candidates here for water barrier, we have a three-dimensional amorphous polymer phase. Today, we're using like 1 to 2% in added value products. And if we could use this in the barrier, this would increase quite considerably. The majority today is burned as fuel in one way or the other one, or added in fuel. And that's a shame, because lignin has quite many great potentials. It's fire retardant, it's UV absorbent, potentially antibacterials and antioxidant, hydrophobic as long as you don't solve it in alkali, it's biodegradable. So we kind of have all the boxes here that we really want. We have some boxes that we wouldn't want. It's quite brittle too. But this comes to the aim of what the work we have been doing, and that is to make a water barrier coating from lignin-based lignin that can be applied in dispersion coater. And this is really where we come into the concept that we have developed. We want to get something like this where you have a water repellent surface, but we should apply it in a water-based system, which is quite tricky. When it comes to lignin, you either solve it in alkali, you can also modify it by sulfonation, carboxylation, and oxidation. And Pedram, who is talking afterwards, can tell you all about these modifications. You can also use solvents. The first two ones, you potentially lose some of the hydrophobic properties of the lignin, so that makes it a little bit hard to do. Solvents, I'll get back to that one later on. The other way around is kind of to trick the system a little bit, that you put the lignin in particles somehow and you suspend them in water. And this is usually done by you're adding some sort of a stabilizer or surfactant that would actually place itself, have one hydrophilic end that will turn towards the water and one hydrophobic end that will turn towards the lignin. We have done other works with dissolving lignin in either acetone or isopropanol, and it works quite nicely. If we look at the next picture here, we actually see that when we had the solvent system, we have a nice melting of the lignin structure here. This is just plain lignin-based lignin after drying, evaporating the solvent. If you have an insoluble system, you get something that looks like this, that is quite a lot of dusty surface that would actually fall off in dust. And I haven't had anyone who has had say, hey, I have a pile of money, I want you to create dust, at least not in paper. Paper concepts or paper industry, you usually want to get rid of that one. Anyway, if we solve it, we can actually make a hydrophobic paper. I know that the Lignin-based, the Lignin movie that Maria sent, I don't know if we actually have a phase where I use a hydrophobic paper, and this is actually something that done 15 years ago, and the papers are still quite hydrophobic. But the interesting part was that when we actually put coating onto it, we increased the strength and the stiffness quite considerably, even at high relative humidity. So for that particular way, it's kind of interesting. The hard part is to put it in water. We also tried to cast lignin films, and most of them ended up like this. Well, one of the problems is that lignin is quite brittle in itself. The other one is to make it dispersed in water, of course, in order to make it film forming. You need both these, and we didn't get that one when we tried to cast this particular one. So what we started to look at was with lignin oils. We actually put together a lignin oil with a modified lignin and vegetable oil with different lignin constants, 35 to 40%. Then we used a surfactant. That would place itself in the interface between the oil phase and the liquid phase or the water phase here. So what you basically do is that they stir around the whole system with oil and water, and you end up with something that looks like one phase, but it's not. So it's a little bit like making a salad dressing in lignin oil, and then we put the surfactant to stabilize it. And we put it on a liner, and we also put it on a pre-coated board where we used regular paper chemicals. We used calcium carbonate from Omia, a quite common one, and styrene acrylate latex here as pre-coating on the backside of the board. We wanted to know what the surface was actually. As I said, what we would do is that we would make a solution in cold water out of the surfactant, Triton X114 or X1110. We would disperse the oil in a homogenizer with a quite high stirring rate, and we would stepwise add the solution into the system here. Or we would stepwise add the water into the system here. We put a water in oil emulsion here. We did coatings, bend coatings, and dried it for 30 minutes first in 105 degrees, and then we had an extra annealing step at different temperatures and characterize it with either putting a drop and observing how it would dissolve into the surface, but we also measured the water vapor transmission rate. And if we look at water in oil, you would actually have the waters as the dispersed phase. In the oil phase, oil and water, you would have the other way around, oil in the dispersed phase. And this is usually what you think about. This is what we have actually tried both of these, but I will only talk about this one actually here. Observations afterwards, you actually get a quite nice surface like this. We could also see that the emulsions were generally stable for a week after the preparation, so we can actually handle them, but it could be better, of course. After the first drying step, the coatings were quite hydrophobic, but there were also pores. So after annealing, we actually get rid of the pores, and we also get a non-stick continuous film. We weren't able to produce two coatings. They wouldn't stick to each other for some reason. And if we didn't have the pre-coatings, we would have problems with the board, that we would actually have the oil penetrating it. When we look at the liner as a pre-test, we would actually have a breakthrough of water drop immediately, to say. When we put the lignin emulsion, we actually didn't have a breakthrough immediately or at all, but we would have an absorption time. And what we can see is that when we had 30% lignin, comparing 150 to 150, we had quite a lot better results when we had 40% lignin. So the lignin content here is quite important. We also can see that when we increase the annealing temperature, we actually increase the time for absorption up to a point of 150 degrees. Above this, we probably destroy the structure a little bit. So that is kind of what we see in this this slide. We had a pretty promising results when it came to drop test. We have a surface that is kind of closed. When we measured the water vapor transmission rate, we got quite promising results. If we look at the baseboard, we have a quite high value here. This is actually the pre-coated board. When we had an annealing temperature of 150 here, we actually had a little bit higher transmission rate than when we went down in temperature. The interesting part here is that this is also yellow rod that is a little bit less deposition than the green rod here. So that is probably part of the explanation here. But if we look at the green rod with the 35% oil, we actually see how it decreases. And when we had the 40% oil, we actually had a better response here. I get a question in the chat whether the lignin is unmodified. No, it's modified actually. So it's not just plain kraft lignin that we mixed. But generally, what we can see is that we get something that is a promising water barrier. It's not a perfect one, but it's at least below 100 grams per square meter a day. So if we can put some sort of conclusion, is that we can actually put the lignin oils in the emulsion, and we can coat board with as a water barrier with promising results. Acknowledgements. Dr. Klabin, Mercer Pulp, Renfrew, and Stora Enso are greatly acknowledged for financial support and also for quite many interesting discussions with them. And I also want to thank my colleagues Fernando Alvarado, Yibing Li, Evelyn Kapanema, and Per Tolmanen for scientific and technical support and many interesting discussions here too. And of course, I want to thank you for your attention here. Any more questions, please let me know.
Thank you, Peter, for a great presentation. Very interesting, and packaging is a hot topic. From the chat, is the product food grade approved?
The quick answer is no. This is an experimental product, so no, we can't say that it's food grade approved. It's not a commercial product.
And can you give more information on the type of modification?
Well, what we have done, and this is something that you usually do when you do a lignin oil, you actually acidify the lignin to some degree, and you mix it with a fatty acid. So that is the information I can give you at this point.
Very interesting. And myself, I'm curious and ask what is the next step?
Well, we are working quite a lot on the stability of the lignin emulsions, and we're also looking quite a lot on how we can get a better rheology to put it, make it more coatable. So that is kind of where we are doing.
Very good. And we have the question, at which conditions were the WVTR values measured?
Standard conditions, 23 degrees centigrade, 50% RH. And I see that when casting lignin films, did you take in consideration drying rate and temperature parameters? Yes, we did. And it did. We tried quite a lot there. We did quite a lot of work on that one, and it turned out to be a dead end. That's really hard. I also see question, did you measure cob? I think that we have measured cob, but I can't recall what the cob showed us actually. I'm sorry about that one.
And have you used different lignins or a specific lignin?
We have used Lignin-based lignin in this craft lignin. We haven't gotten to the point where we actually have tried other lignins. So that's of course something that would be interesting to do. And I hope that we can do it quite soon too. So
very good. And could it be used in spray application on molded fiber?
Well, it depends if we can get the rheology to work. Otherwise, I don't see a problem with that. But we need to get the rheology. And when it comes to spray, you really need a low viscosity. And for that particular part, emulsions might actually be quite good if we can increase the water content, of course.
And complement excellent presentation. Wondering, how does lignin react with hydrogen as a gas?
I have no idea. Sorry to say that, but maybe Pedram can answer that one.
We see. Pedram, are you with us and awake?
Yes, but can you repeat the question, please?
Yeah, sure. And welcome to you, Pedram, because you will give us a presentation very soon, and you are in Canada, where it is morning right now.
Early morning, yes.
Yeah, and the handover question was, how does lignin react with hydrogen as a gas?
Well, that question also came to me 2-3 days ago. We are searching for papers to see who did what. I don't have a direct answer yet, but I will be having some answers in a day or so. I have asked my students also to see what, not just how it reacts, what's the history, if you have any evidence that people did on this or not. So if you have, well, I can send the papers, whatever I received to you, and you can send to others, please.
Very good. Thank you, Pedram. And you're now on to give us a presentation also, and we look forward to that. And as we can see from the questions, there is more research opportunities to take care of. A lot to do in the future. Opening.
So
would you like to share your presentation?
Sure.
Pedram?
Okay, so
yeah, sure. And introduce yourself also.
Sure.
And thank you, Peter. I agree on everyone typing excellent presentation. So thank you, Peter. And for everyone having more questions to Peter, continue to type them in the chat. Peter will have a look at them. And also, as we said afterwards, we will stay and we can have a chat together. So Pedram, please go ahead with your presentation.
Sure. Well, thank you very much. First of all, Mario, LignoCity, and other people who invited me to present at this seminar. It's really great honor to share with you my findings. Basically, I've been involved in different products production from lignin, and lignin dispersant in one of them. I'm Pedram Fatehi. I am a professor of chemical engineering department and a Canada researcher in the same department, and also director of Biorefining Research Institute at Lakehead University in Canada. So here we are, well, early morning, it's 8:35 my time. I hope that wherever you are doing great, and you will have a fantastic day or night. So first of all, why lignin dispersant and challenges, opportunities? I will discuss a little bit what's going on in this on this topic and what's our latest achievement. So first of all, current use and application of lignin, basically dispersant. So at least in Canada, I'm sure that in Nordic countries, we have the same story. If you go to retail store and you want to buy new paint, stain for residential area, when you open them, they don't smell, which is a good thing. So that means that they do not use solvent in paints, and they are water-based. So water-based paint needs water-based dispersant so that all pigment, everything is homogenized in the system. So they need basically new water-based dispersant for this paint, stain and dye and this type of system. In fraud flotation of mining industry, where they make bubbles to generate, to separate the minerals, the desired minerals from the rest, the viscosity is important, the yield is important, and they use dispersant to reduce the viscosity while keeping the water content of their system at some level. So dispersant plays a big role over there. In construction industry, especially in cold climate countries like Canada and Nordic countries. So basically, water reducing agent is an important aspect. We want to have the concrete, cement, paste with as minimum water content as possible because of the freezing problem, because of handling, because of cost, and so many other factors. But there is a limitation because we don't want to change or affect the flowability and workability of cement. So dispersant is a has a big role in cement and basically concrete. Textile industry, again, when we have dyeing processes, we want to have all the dyes suspended, basically evenly in the solution, and dispersant plays a big role preventing agglomeration of dyes and helps the dyeing process. Ceramic industry, again, we have a lot of ceramic-based product, and clay suspension is a big topic, an important factor, and dispersion of clay particles in the suspension is really important. So if you look at this application, and these are some, we will have a lot more. If you look at them, they are we are talking about big market, and so the market demand is really high. But they currently use chemicals. Some of them I brought them here. Some of them, for example, polylactic acid, polyphosphate, sodium naphthalene. They are expensive. They are oil-based, so they are not really meeting the demand of sustainable products. But what's the opportunity? So lignin opportunities. So we have abundant lignin resource in agro and wood-based material because basically lignin roughly is around 1/3 of biomass. So it doesn't matter if it's agro-based or wood, it's roughly around one third of biomass. And if you look at the LignoBoost, LignoForce technology from the craft process or other technologies that have been introduced in the market, lignin can relatively be easily separated from the rest of the pulping or other cellulosic-based processes. So lignin can be and has been commercialized for commercial use, and basically lignin is available at commercial scale. So the other thing that I want to point out is that we have other biorefining-based operations, for example, for cellulose, for hemicellulose of lignocellulosic material, but we cannot economically and feasibly have a commercial process that utilize only cellulose and hemicellulose, and lignin need to be dealt with. So, and because the mass of that one is really huge, so there must be some alternative for lignin utilization in whatever processes we have if we want to have the biorefining operations technically and feasibly meaningful. So, but there is a big research gap in lignin conversion and utilization. So that's why we need to utilize lignin, and because the market for dispersant is huge. So that's why I studied lignin-based dispersant production for over 10 years. But what is available, or if you look at the literature, do we have lignin-based dispersant? Yes, lignosulfonate. Lignosulfonate, there are some reports that lignosulfonate was used as a dispersant for some suspensions, but the problem is that the sulfide pulping processes are not dominant, and they are getting close one by one. So production is an issue, and we have only one group of sulfonate group on the lignin. So the charge density and the sulfonation degree of lignin for lignosulfonate is limited, and the material you get has some sugar, and that has been problematic for some application because it's not pure. So I discuss about all of this in one of the review paper I published. If you are interested, you can look at that. So, but if you want to produce dispersant, there are different methods, but there are two main methods that I want to discuss today, and I want to compare them a little bit and see how we can produce them. So let's move to oxidation. So when you look at the literature about dispersant production, people talk about the charge density and molecular weight of dispersant. So the first thing we did was to see how molecular weight and charge density of dispersant can affect its performance. So to make dispersant or charged low molecular weight lignin, we tried nitric acid because it's easy, it can decompose lignin easily, and our suspension model kaolin was kaolin clay because it's available everywhere. So in this set of experiments, we generated 10 different samples. One batch, they had similar molecular weight, but different charge density. Another batch, which is on the right side, different molecular weight, but the same charge density. So in this way, well, of course, we had many different reactions, but this is how we categorize the product of this oxidation reaction. And what we noticed is that, so we had 10 different samples plus the unmodified lignin, and then we applied different dosage of each one to clay and basically studied its dispersion, or basically relative turbidity of the suspension. So relative turbidity is an indicator of the dispersion of the sample. So what we noticed is that first, by increasing the amount, the added amount to the solution, the adsorption would increase and the turbidity will increase. So that's what we noticed in both batches. But if you look closer, so here OL5 has higher charge density than OL1, and this is the order of increasing charge density. This is the order of increasing the molecular weight. What we noticed is that the higher charge density sample generated better results. But for the molecular weight, at some point, it started to reduce its, it started to lose its efficiency. And that's because when you have larger and larger molecule, they start to coagulate instead of disperse. So the higher charge density, the more strength of repulsion. So that's a good thing. But molecular weight, you need to be careful because you can't go beyond one level. So we moved on. So we studied hydrogen peroxide, and for hydrogen peroxide, again, we wanted to see if we could produce dispersant, and we did. And if you can see, again, the experiment was easy. We had lignin, and all of the lignin I have was either from LignoForce or LignoBoost. So they are pure lignin. So we just did the alkaline peroxide reaction, atmospheric condition, and we can see that our oxidized lignin behave much better than lignosulfonate that was claimed to be used as dispersant. So that was a good start. But the question was, peroxide is a bleaching chemical. So what are the properties of PSH lignin extract? Is it worth investigating? So I'm just bringing that question if you're interested. So is the lignin that's generated from this stage has some dispersant properties. So we moved to grafting. Here we tried many different grafting routes. So basically with different carboxyalkylation, for example, from 1 carbon to all the way to 15 carbon, because we wanted to see how this carbon chain affect the properties. And we noticed a big difference in terms of adsorption when we studied the adsorption of the same material. So we had the same material, but with different charge density. We noticed that the thickness of this material that is adsorbed on the surface, on our model surface, is different. So the charge density, the alkyl chain will play a big role in the thickness of the material, in the thickness of the lignin that's absorbed on the surface. And that will impact the dispersion properties significantly, because it makes a coating layer on the particle, and with different mechanisms, it can, disperse particle in the solution. I will get back to the mechanism later on. For the cement, basically admixture, again, lignosulfonate has been used for this application. We wanted to make sulfonamethylated lignin that has similar properties to lignosulfonate, but we couldn't just sulfomethylate lignin. We saw some difficulties. So first we oxidized the sample to open up the structure, and then we did the sulfomethylation. What we noticed was that by increasing charge density of the product, we got much better fluidity. I will talk about fluidity in a second. And the performance of our product was much better than, again, the two different lignosulfonate samples that are available in the market and are claimed for the same purpose. So what is fluidity? Fluidity, you make a mixture or paste of the cement, you put in this cone, and then you pull up this cone, and you let the paste spread, and that's called slump test. And then you measure the diameter of the circle that's generated. And the larger the diameter, the higher the fluidity. And that's very important for workability of the cement. And it's an indicator of the rheology and viscosity of the suspension. So the point is that we generated the sample, and they work really greatly. So we tried different sulfoalkylation. And what we noticed was that it really matters how you sulfoalkylate lignin, even if you manage the same charge density, even if you manage the same, let's say, sulfur content. It really matters how you, what chemistry and how you modify the lignin. And again, some other people try different, again, sulfoalkylation, and what they realize is that by extending the chain length, you are making a little bit higher molecular weight, and then you will decrease the agglomeration because of the dispersion and so on. So, and that's another group proving our point. So altogether, what we realized, and that's very important aspect, is that the absorption of whatever lignin-based dispersant you produce on the particle is very important, because unadsorbed dispersant that is available in the suspension, they don't work, they don't function. So what matters is that adsorb level. So surface coverage of the particles in the suspension is very important. So you need to design somehow to have a really good interaction. Too thick layer of your lignin-based dispersant could make a coagulation instead of dispersion, and too thin layer would not help. So that will affect how you design your lignin-based dispersant. And of course, the thickness will be a function of particle size. But the other thing is that I'm not sure if you need to have a soluble lignin or not for some applications. So these are the mechanisms of dispersion. When you do oxidation, so the first one is the charge repulsion. So what we do is that we add material, we add lignin-based dispersant in the system to introduce some charges to repel particle. The other one is that due to hydrophobicity of the lignin, they can agglomerate. But if you improve the hydrophilicity of lignin, that will help the dispersion. So that's the second approach. The third one is steric hindrance. So that means that you absorb something on the particle so that this particle, the big particle, cannot agglomerate. When you do oxidation, the first two are targeted basically, but when you do grafting, all three are affected, and that's very important. So again, I have 3 more slides to finalize this. So what we notice out of oxidation, we have done a lot of hydrogen peroxide, peroxide, nitric acid, oxygen gas, and so many different approaches for making lignin-based dispersant out of oxidation. Usually they introduce carboxyl group, they open up ring, phenolic ring and CC bonds. They reduce the molecular weight, but this could be a necessary step for other modification, which if you want. But they kill the 3-dimensional structure of lignin. That's very important. So when they are smaller and they don't have the 3D structure, maybe you need to have a higher dosage to have them disperse to have them have a good dispersant. And this approach is not utilizing the 3D structure of the lignin. So, on the other hand, when you oxidize the lignin, yield is important and filtration. They may contribute to the cost of production of lignin-based dispersant. But this approach, oxidation, can be utilized in the craft pulping process. Integration is not an easy. How about grafting? Again, we have done a lot of sulfur-alkylation, carboxyl-alkylation, amination. You can introduce many different charges, not just carboxylic group. They increase the molecular weight a little bit, not too much. Different chemicals can be targeted. So you can target phenolic group, you can target aliphatic group, you can have different chemistry. Yield is not an issue because you are adding chemicals to lignin. You are not decomposing or degrading or basically cleaving the lignin. The structure of lignin is not affected, and this is very important for thickness development when you want to have dispersant. So its phenolic group is not much affected. The 3D structure will be there, but production cost, again, depending on the chemical you want to use for your reaction, the production cost may be cheap or may not be cheap. So in terms of integration, some of them can be integrated into the craft pulping process or other pulping processes, but you may need some external chemicals. So, but because they are more effective, lower dosage of them are generally needed than the oxidized ones. So the compromise is that the lower dosage is needed, but the production cost may be, not all the time, may be a little bit larger. So overall outcome, we have done a lot of routes and we know how to produce dispersant following different routes. So some of these, what we have produced are at the scale of operation, and we are working on that. So how we know? Because of the reaction performance, we know they are easy, we know how the yield is, and the other factors, we know how they function as a dispersant. So these two are very important: reaction performance, dispersion performance, and we have some products that are good. So, and the other point that I want to bring here is that dispersant production is not just controlling the charge density and molecular weight. There are other factors about lignin that needs to be considered. There are two methods of commercialization. One is the integration, and in this case, some of the sulfur-alkylation and carboxyl-alkylation can be easily integrated because the chemical that we add are well in harmony with the chemical of craft pulping process, so they are not introducing any new element to the chemistry of recovery process and so on. But again, the raw material and waste management should be considered. Or you can have the lignin separated following LignoBoost, LignoForce, and then have the modification totally separated in another company. Again, we have some options for that, and some of them are really great to follow. The last slide is that I don't think the dispersant production should target only one market or one product. You can produce different products, like switching from hardwood to softwood, sometimes for this application, sometimes for that application. But the good thing is that the same facilities can be used for producing dispersant for different products. What's coming in future? Well, dispersant are used in dye and paint formulation. We haven't finalized that. Cement is still is a thing to go. Mineral processes, the other two ones. Cold water slurry is a big topic now. It's gonna be a new, it's gonna replace coal and Pickering emulsion. Basically emulsion, we have a lot of oil, water emulsion for cosmetic, for many applications, and that could be another application of dispersant. So collaboration, well, if you're interested in lignin-based dispersant, I would be more than happy to discuss with you, either if you wanna get involved in what we are scaling up or commercializing, or understanding the fundamentals of lignin-based dispersant. So I would like to thank all of the partners who have helped us with the technical and financial aspects, especially FB Innovations, NSERC, Resolute, and others who have helped us a lot. Thank you very much.
Thank you, Pedram. Great presentation. And some questions has been popping up in the chat. I don't know if you have it open and see for yourself. First, we had if you talk about only craft lignin or also lignosulfonates, and you touched both.
Well, we have tried craft lignin. We have tried lignosulfonate. So basically, lignosulfonate has one sulfonate group. We try to improve it, increase it. It works. So dealing with lignosulfonate, I can't tell if it's easier or harder, but it's, because it's soluble material, it's different.
And then there is a comment about that lignosulfonate has been a commercial product since the mid-1930s as a dispersant.
Yes. So well, again, dispersant, again, I brought that, the problem of lignosulfonate is because, well, it cannot saturate the dispersant market. Okay, so we have a huge market for dispersant material, and that cannot meet that. The other one is that its functionality is limited. You know, if you look at some of the slide I had, always compared with lignosulfonate, because, well, we wanted to have a base, and no, we can do better. So that's the point. The other one is that, well, lignosulfonate at least has been used in 2 mineral processes in Ontario, and after some time they came back and said that the sugar content of lignosulfonate is really problematic because it's not a pure material. And if you want to make lignosulfonate a pure product, the cost will go up dramatically.
And what are the prospects for lignosulfonates in future? Will these still be available as byproducts from the paper industry in future?
Well, I don't know. That depends on the sulfite pulping process, you know, all the economy of that. I personally do not think that it will disappear, because it may have its own advantages for some especially paper. But I think its production will go down if it only depends on the sulfite pulping process. But if somebody makes some value-added product out of lignosulfonate, they can have, you know, a smaller operation just to target to produce lignosulfonate out of wood, and basically generate other cellulosic-based material, not paper, other cellulosic-based material, to have a biorefining. So let's say sulfite-based biorefining, we could have it in future.
Right. And what is your opinion about lignin as a chelating complexing agent?
Chelating, well, we have been doing that. I did not bring that up. There are some reports. We have also studied the interaction of lignin and or modified lignin with different elements. Yes, you can, but in terms of interaction, I don't think there is any problem. We have seen that and we have improved that. But generally, the filtration and removal of the lignin from the system is an issue. If you leave it with the pulp, for example, that could be an option if you're talking about unbleached pulp. But if it goes to the bleached pulp, because of the color of lignin, there should be some advancement. Having said that, we have worked on some lignin, enzymatically produced lignin, that are not brown. So not brown. So for that application, I think that type of lignin, let's say out of mechanical pulp, that could be an option.
The commercial global market for lignosulfonate is approximately 1 million TPA.
Yes.
Yeah. And with that said, we have like 2 minutes left from the 1 hour, and I think we have spent it very well. And the 15 minutes after, when we will have a chat, we will not record, but this recording of this webinar will be presented on the webpage of LignoCity, so everyone can look at it several times and spread it to your friends. And I thank you very much to Pedram and Peter that has been presenting today, and to the audience. We have been nearly 100 persons live watching, so that is great. Thank you everyone for your interest in lignin and its possibilities. So with that said, we say thank you from the LignoCity webinar, and we stay, whoever wants to have a chat, and then I want you all to turn on your cameras instead. Thank you, Pedram, and thank you, Peter.
Thank you very much for the time and for the opportunity.